Okay, picture this. You're in a massive freezer, rows and rows of frozen goods stretching into the distance.
Hmm,
Or maybe you're in a bustling restaurant kitchen, steam and heat rising from the grills.
right.
You see the sprinkler pipes above, and your brain goes, fire protection, got it. But the truth, revealed by our source material today, deep dives into NFPA 13, the definitive standard for installing sprinkler systems, is that fire protection in these places is wildly different from your office building or home.
Oh, absolutely. It's a whole different ballgame.
It's a complex, fascinating world of specialized systems, each engineered with incredible precision to tackle unique environments and specific fire risks.
That's absolutely right. NFPA 13 isn't just one set of rules for one type of system.
Yeah.
It's really a blueprint for tailoring protection.
Tailoring, yeah.
It addresses everything from how you prevent ice plugs in pipes that are below freezing, to how you ensure a grease fire is suppressed instantly at its source, to protecting a building not just from fires inside, but from one raging outside.
And that's our mission for this deep dive. We're going to peel back the layers on these specialized sprinkler systems.
Get into the nitty-gritty.
Exactly. We'll look beyond the familiar, understand what makes each system tick, and, crucially, get to the why behind the intricate, sometimes counterintuitive requirements that the standard lays out.
Yeah, the why is key.
It's about seeing the clever engineering solutions that keep us safe in places you might never have thought about.
We're going to see how something as simple as, like, a tiny hole in a valve clapper can be a critical piece of design,
Right.
or why a sprinkler head in a freezer might need a detector activating before it does. It's fascinating stuff.
Right, let's unpack this. Starting, as you said, with the most common system, just as a point of comparison.
Right, the wet pipe system. It's the standard. You see it everywhere.
The default, basically.
Pretty much. Simple concept.
Yeah.
Pipes are kept full of water under pressure all the time, right up to the sprinkler head.
Okay.
When a fire happens, the heat activates the sprinkler head, it opens, and boom, water flows immediately.
Instant gratification in terms of fire suppression. Water is right there, ready to go.
Exactly. It's the fastest response possible with a water-based system.
Yeah.
But, even for this baseline, NFPA 13 has specific requirements. Take pressure gauges, for instance.
Right, they're not just stuck on anywhere.
Not at all.
Yeah.
You don't just put them anywhere. They're required in very specific, critical locations. You need one in each system riser.
Which is the main pipe coming up.
Yeah, the main vertical pipe bringing water up, so you can see the main system pressure.
Okay, that makes sense.
Yes. But you also need them above and below things like alarm check valves or cistern riser check valves.
Why both above and below a valve? What does that tell you?
That's key. It allows you to verify that the valve is properly holding pressure.
Oh, okay.
If the pressures above or below are significantly different when the system is idle, it could indicate a problem, like the valve isn't sealing correctly.
All right.
And when the system is activating, you'll see a pressure drop above the valve as water flows, and checking the gauge below confirms the supply pressure is still there. It's like taking the system's pulse at vital points.
Got it. Monitoring integrity and operational status. What if that pressure gets too high, say, from heat expansion?
That's where a relief valve comes in. Wet pipe systems, especially if they have a check valve, like a backflow preventer that stops water from flowing back out.
Creating a closed loop, basically.
Exactly. They can build pressure due to thermal expansion. The water in the pipes gets warmer and expands. NFPA 13 requires a relief valve to handle this.
Okay. What are the specs on that?
It must be at least a ½ inch in size and said to open at 175 pounds per square inch, PSI, or 10 PSI above the maximum system pressure, whichever value is higher.
So it's a safety release to prevent the system from literally bursting under pressure.
Precisely. It protects the pipes and fittings from potentially dangerous overpressure conditions caused by that thermal expansion in a closed system.
The source mentions you can skip the relief valve sometimes.
Yes, that's right. The relief valve isn't required if the system includes auxiliary air reservoirs.
Air reservoirs, how do those work?
They act as pressure buffers. As the water expands, the air in the reservoir compresses, absorbing the pressure increase without needing to release water.
Interesting alternative approach, a sort of shock absorber for pressure.
Kind of, yeah.
Can a wet pipe system feed other types of systems, like the more specialized ones?
Yes, it absolutely can. A wet pipe system is permitted to supply water to smaller, auxiliary dry pipe, preaction, or deluge systems.
Oh, okay.
The crucial caveat is that the overall water supply has to be sufficient to meet the demand of all systems it's feeding simultaneously under fire conditions.
So the fundamental wet system can be the backbone for more specialized zones, provided the supply is big enough.
Correct.
Now, dealing with cold is a major theme here. Even for wet systems, there's a rule about preventing freezing near valves.
There is, and it's very specific. You cannot use electric heat tracing cable wrapped around the pipe or valve instead of providing a permanently heated valve enclosure.
So no wrapping it in heat tape like you might on a water pipe at home.
Right. Not for these critical valves. You need a little heated room or cabinet for the valve.
A dedicated heated space.
Exactly. Heat tracing might prevent freezing on a pipe run, but for critical control valves, the standard requires a more robust, reliable solution. A permanent, dedicated heat source within a protected enclosure.
Why the strict rule?
These valves are the gatekeepers for the entire system. Their operation cannot be jeopardized by a potential heat trace failure in cold weather. It has to work when needed.
That makes a lot of sense. You need the most reliable method possible for those critical components.
Right, and here's where it gets really interesting. A specific requirement for wet pipe systems that use metallic pipe is that they need a single air vent.
An air vent on a pipe full of water. That sounds counterintuitive. Why would you vent air out of a water pipe?
It does, but think about how pipes are filled. Air can get trapped in high points or along horizontal runs, especially in metallic piping systems where you might have internal pipe wall irregularities.
Okay, little pockets of air.
Right. And these trapped air pockets can cause several problems. They reduce the volume available for water, potentially slowing down initial flow to a sprinkler head.
Which you don't want.
No. And over time, trapped air contributes to corrosion inside the pipe when in contact with water.
Ah, corrosion. That makes sense.
So a single air vent, typically located at a high point on the system, allows this trapped air to escape as the system is filled or repressurized. It ensures the pipes are completely full of water for optimal performance and longevity, and helps mitigate internal corrosion.
That is a fascinating detail. A tiny vent to prevent seemingly small issues that can have big impacts. Wow.
It really highlights the depth of consideration in the standard. Even the most basic system has these engineered nuances.
All right, let's transition to systems where freezing isn't just a potential problem, but the default environment. Dry pipe systems.
Okay. Dry pipe systems are designed specifically for unheated areas subject to freezing.
Places like unheated warehouses, attics, parking garages.
Loading docks and cold climates, exactly. The pipes in these areas are filled with compressed air or nitrogen instead of water.
Okay, so air in the pipes. Where's the water?
The water is held back in a heated area by a specialized dry pipe valve.
Got it.
When a fire occurs and a sprinkler activates, the air pressure in the pipe drops rapidly. The dry pipe valve trips open, and then water flows into the piping network and out the activated sprinkler.
So it's a deliberate two-step process. Air escapes, then water fills the pipe and flows out.
Right.
That introduction of a delay is the trade-off you make to avoid freezing.
Exactly. And because of that necessary delay, monitoring and managing the system's air pressure is absolutely critical. Pressure gauges are required in many locations.
More gauges. Where do they go on a dry system?
You need them on both the water side and the air side of the dry pipe valve itself.
Okay, checks and balances on the valve itself.
Precisely. To confirm, the water supply is ready and the air barrier is holding. You also need gauges at the air compressor, the air receiver, if there is one, in each independent pipe connecting the air supply to the dry pipe system and at any quick opening devices.
Wow, that's a lot of monitoring points.
It is. Monitoring pressure at all these points is vital for ensuring the system is set correctly, detecting leaks, and troubleshooting any issues.
What about the sprinklers themselves? Are there restrictions on the types you can use in dry pipe systems to avoid that trapped water issue again?
Yes, absolutely. Again, focused on preventing water from getting trapped where it can freeze. Upright sprinklers are generally fine because they naturally drain.
Water just falls out.
Right. Listed dry sprinklers are specifically designed for this application. They have a seal way back at the butt end, in the warm area, that prevents water from entering the unheated portion of the pipe until the head activates.
Okay, those make sense. Built for the job. But what about pendant or sidewall sprinklers? They hang down, seems like they'd trap water.
They are prone to it. Pendant and sidewall sprinklers are only permitted under specific conditions.
Such as?
Either they must be installed on return bends, i.e. the sprinkler head itself, the return bend, and the short section of branch line piping connected to it are located in an area maintained at or above 40 degrees Fahrenheit.
So you use a return bend to loop that little section of pipe back up into a warm space. Clever.
Correct. Any water that gets into that small section, whether from condensation, a test, or minor valve leakage, drains back into the main dry pipe or stays in the heated area where it won't freeze.
Okay. What's the other option?
The other permitted scenario for pendant or sidewall sprinklers is if the sprinkler and branch line are in an area above 40 degrees FER, the water supply is potable. And the piping used is either copper or CPVC that is specifically listed for dry pipe applications.
Got it. Copper or CPVC listed for dry pipe in a heated area with a potable supply. It seems like every single rule is designed to ensure no water sits stagnant in the cold pipes.
That's the driving principle for dry systems. Now, a really detailed area in the standard is the size of dry pipe systems. This gets complex because the size directly impacts that water delivery time, which needs to be managed.
Right, the delay. You mentioned a 60-second rule earlier for water delivery. Is that the main constraint?
That's one option, yes. The system must deliver water to a specified test connection in no more than 60 seconds from the time the test connection is fully opened and the system starts at normal air pressure.
Okay, 60 seconds to the test point.
But there are other ways to comply, often tied to system volume, the total amount of air in the pipes. A dry pipe system with a volume of not more than 500 gallons.
That's about 1,900 liters.
Right. That size is permitted without requiring a quick opening device. And it's not required to meet any specific water delivery time to the test connection.
So for smaller volumes, the inherent delay is considered acceptable without extra measures. Seems reasonable.
Yes, under 500 gallons. A slightly larger system, up to 750 gallons, around 2,800 liters, is also permitted without meeting a specific water delivery time, but only if it uses a quick opening device.
So a QOD lets you have a slightly larger system volume-wise without needing to prove the 60-second delivery time.
Correct. The QOD helps mitigate the increased delay caused by the larger pipe volume. It speeds things up.
Okay, what else?
The source also allows another way. The system size can be determined based on hydraulic calculations specifically for water delivery time.
Performance-based design, then.
Exactly. This uses a listed calculation program and method based on the hazard being protected, referencing a table in the standard that lists different fire risk levels from dwelling units up through high-piled storage.
So you calculate to ensure water gets there fast enough based on the fire risk itself.
Precisely. The calculation here measures the time from when the most remote sprinkler sectors are expected to open to the time pressure at that sprinkler reaches and maintains the required design pressure.
That sounds like a very specific engineering calculation, not just a stopwatch test.
It is. Now, there's a particularly strict rule for dry pipe systems protecting dwelling unit portions.
Like if an apartment building or hotel has unheated areas, say an attic or crawl space, protected by dry pipe?
Yes, exactly. For any dry pipe system protecting dwelling unit areas, the initial water discharge from the system test connection must occur in not more than 15 seconds.
15 seconds? That's way faster than the general 60-second rule.
It is, much faster. And these systems protecting dwelling units cannot use the 500 or 750-gallon volume exemptions. They must meet that 15-second time limit, demonstrated either through calculation or testing.
Wow. Why so much stricter for dwellings?
Well, the standard doesn't explicitly state the reasoning, but it's likely tied to life safety. Fires in residential spaces can impact occupants very rapidly. Faster sprinkler response is critical for escape and limiting fire spread, especially in potentially smaller, compartmentalized areas.
That stricter limit makes sense from a life safety perspective. You need that water there almost immediately once a sprinkler opens in someone's living space.
Precisely. That 15-second limit applies to water delivery time to the single most remote sprinkler for dwelling unit calculations as well.
Okay. The standard also outlines another alternative method for determining system size compliance called the manifold test connection. How does that work?
It's a way to physically test the system's performance more realistically, perhaps. Instead of just opening a single test connection, you test through a manifold setup that simulates the flow from multiple sprinkler heads expected to operate for a given hazard.
Like simulating a real fire scenario better.
Yes, simulating maybe 2, 3, or 4 sprinklers opening. You must demonstrate that initial water discharge from this manifold is no more than the maximum time specified in that same hazard table we discussed. Table 8.2.3.6.1, starting from normal air pressure and with the manifold fully opened.
So you're physically proving the system can deliver water fast enough for the expected fire size, not just to one point.
Exactly. If you meet the requirements using this manifold test method, you don't need to meet the 60-second rule or the calculation rule. It's an alternative path to compliance.
Flexibility in how you prove performance.
Right. The standard also notes that dry pipe systems with different water delivery times can be acceptable if they are tested and listed for that specific performance. Allows for innovation.
Let's talk about splitting up dry pipe systems. The source says you generally can't subdivide them using check valves unless they're in a heated enclosure. Why not?
Right. A check valve outside a heated space could trap moisture or small amounts of water between it and the main dry pipe valve. That trapped water could freeze and block the system or cause damage.
Makes sense. So if you do use check valves for subdivision, they have to be in a heated box or room.
Correct. They must be located within a heated enclosure.
And here's another one of those incredibly specific details. When check valves are used for subdivision in heated enclosures, they need a tiny hole.
Yes, a 332-inch, which is 3 millimeters hole, must be drilled in the clapper of each check valve used for this subdivision purpose.
A hole in a valve meant to stop flow. Again, that sounds completely backward.
It does seem odd at first glance, but it's brilliant engineering. That small hole allows air pressure to equalize slowly between the different sections of the system divided by the check valve.
Equalize air pressure. Why?
Without it, minor air leaks or temperature changes could create slight pressure differences between the sections. This could potentially cause nuisance trips of the main dry pipe valve, or problems with the pressure supervision system thinking there's a leak.
Ah, so it prevents false alarms or trips due to minor imbalances?
Exactly. The hole allows pressure to balance across the check valve while still preventing rapid air loss or water flow during normal operation. It's a clever solution to manage air pressure dynamics across system segments.
That is a fantastic example of the level of detail in the standard and the clever solutions employed. It really shows the engineering thought process. Just amazing.
It absolutely does. The source also requires that if auxiliary drains aren't provided for each subdivided section, you need an approved indicating drain valve, which should be supervised closed, connected to a bypass around each check valve, specifically for draining those individual sections.
Makes sense. You need to be able to drain any part of the system for maintenance. What about gridded dry pipe systems? You see gridded layouts in wet systems sometimes.
Explicitly not permitted for dry pipe.
Just a flat no. Why?
Unlike wet systems where gridding can optimize flow, the complexities of managing air pressure, ensuring timely water delivery to all points, and achieving complete drainage in a gridded dry system are simply considered too problematic according to the standard. Too many potential points for trapped water or air issues.
Okay, keep it simple with tree or loop layouts for dry pipe. Let's go back to quick opening devices, or QODs. You mentioned they help with water delivery time?
Yes, QODs are listed devices, permitted specifically to accelerate the tripping of the dry pipe valve and help meet those water delivery time requirements. We talk about the 60-second rule, calculations, manifold test, or other listed criteria.
How do they work?
When a sprinkler opens and the air pressure in the system starts dropping rapidly, the QOD senses this significant pressure drop. It then quickly vents the air from what's called the intermediate chamber of the dry pipe valve. This rapid venting forces the main valve clapper to trip open much faster than it would just from the system pressure dropping alone.
So it speeds up that critical transition from air to water. Where do they connect?
They must be located as close as practical to the dry pipe valve. The connection to the system must be above the priming water level of both the dry pipe valve and the QOD itself when the system is set.
Why above the priming water?
To prevent priming water, that small amount of water sometimes used to seal the valve or minor amounts of moisture from getting into the QOD's internal parts prematurely. That could cause corrosion or malfunction. They need to stay dry until needed.
Right. Keep the sensitive bits dry.
Exactly. If there's a valve installed between the dry pipe riser and the QOD, say, for maintenance, it must be an indicating type valve, and it must be sealed, locked, or electrically supervised in the open position.
Ah, a safety interlock. You don't want someone accidentally closing that valve and disabling the QOD.
Absolutely critical. You
Yeah.
never want that valve to be accidentally closed.
That's a vital protection.
A check valve is also typically required between the QOD and the intermediate chamber of the dry pipe valve if the QOD needs protection against submergence after system operation.
Submergence.
Yeah, after the main valve trips and water fills the system, this check valve prevents that water from flowing back into the QOD, potentially damaging it. If the QOD's design actually requires pressure feedback from the intermediate chamber, then an indicating valve that can be locked or sealed open is allowed instead of a check valve.
Lots of specific plumbing details to ensure it works only when intended and doesn't get damaged. What about preventing water from accidentally entering the QOD from the riser side before it's supposed to?
That's handled by a listed anti-flooding device. One is required in the connection between the dry pipe riser and the QOD, unless the QOD is listed as not needing one or has built-in anti-flooding features.
And its job?
Its purpose is to prevent water from entering the QOD improperly during setting, testing, or maybe from minor pressure fluctuations or condensation in the riser.
Okay, keeping water out is a constant theme for dry systems and their components. It seems like half the battle.
It really is.
Now, where does the dry pipe valve itself go, and how is it protected? The heart of the system.
The dry pipe valve and its supply pipe are critical system components and must always be protected from freezing temperatures and mechanical injury. They are almost always located in heated valve rooms.
Dedicated rooms again?
Yes. These rooms must be adequately lighted and heated. Crucially, the heat source must be permanently installed. Just like with wet system valves, heat tape is not a permitted substitute for reliable, permanent heat in the valve room.
Consistency there. Critical components in cold areas need robust, permanent heat. No shortcuts.
Yes. If there is a sprinkler head located within the dry pipe valve enclosure, which is often done for fire protection of the room itself, its water supply can come from the dry side of the system.
Meaning it only gets water when the main valve trips.
Right. Or its supply can come from a separate wet pipe system, specifically protecting that room.
Providing redundancy for protecting the vital valve area. Smart.
Very. The source also mentions protecting against a high water level for some dry pipe valves. What's that about? This is mainly for dry pipe valves that use a pressure differential to hold back water. They're called differential dry valves, or where the valve design allows it to potentially reseat after tripping without fully draining all the water above it.
Okay. Why is high water a problem there?
If water accumulates above the valve clapper, it reduces the effective pressure differential holding the clapper closed. This makes the valve more prone to false tripping from minor system air pressure drops. Plus, that water could freeze and damage the valve in cold weather.
Ah, so it compromises the seal or risks freeze damage.
Exactly. So, NFPA 13 requires protection against this accumulation, using either an automatic high water level signaling device, basically an alarm, or an automatic drain to get rid of the water.
Okay. Addressing a specific risk for certain valve designs. Let's talk about the air pressure itself and the supply system for dry pipes. The source clarifies air can include nitrogen or other approved gas.
Correct. Whatever gas is used, the pressure must be maintained continuously, year-round.
All the time.
All the time. The supply must come from a reliable source that's available at all times and has enough capacity to restore normal system pressure within 30 minutes after activation or testing.
30 minutes to recover pressure. That seems reasonable.
Yes, assuming it's not a major leak, of course. There's an exception for refrigerated spaces maintained below 5 degrees Fahrenheit, Centigrade 15 degrees C. In those really cold spots, that recovery time is extended to 60 minutes.
Ah, okay. Given our focus on keeping water out of cold areas, that refrigerated space exception is important. Takes longer to refill the pipes, perhaps, or maybe condensation is more of an issue.
Possibly. The standard doesn't specify why, but it acknowledges the unique challenge. The goal with the air supply, especially in cold areas, is to minimize moisture entering the system.
Right, dry air is key.
Absolutely. The air supply connection must be at least half an inch in diameter and enter the system piping above the priming water level of the dry pipe valve.
Above the water line in the valve.
Yes. A check valve is required in this connection, with a listed or approved shutoff valve, like a ball or renewable disc valve, on the supply side of the check valve. This setup controls the flow direction, keeps air going into the system, not out, and allows isolation of the air supply for maintenance.
Is a relief valve needed on the air supply line itself before it gets to the system?
Yes. An approved relief valve is required between the air supply source, like the compressor, and that shutoff valve. It's set to relieve pressure at least 10 psi above the normal system air pressure, but it can't exceed the air supply equipment manufacturer's limits. This protects the air supply components, compressor, receiver, etc., from overpressure.
Makes sense. Protection for the equipment. What about automatic air maintenance? Keeping the pressure just right.
If the air supply is automatic, say, from a plant-wide system, or a dedicated compressor with a storage tank or receiver, then a listed air maintenance device is generally required.
What does that device do?
It precisely regulates the air pressure, feeding small amounts of air as needed to compensate for minor leaks and maintain the correct set pressure without constantly cycling the main compressor.
Okay. Are there exceptions?
Yes. If a compressor serves a single dry pipe system and has a small capacity less than 5.5 cubic feet per minute, then neither an air receiver tank nor an air maintenance device is required for that specific single system.
So smaller, dedicated compressors feeding just one system are exempted from needing the extra maintenance equipment. Simpler setup.
Right. What if one air supply feeds multiple dry pipe systems?
In that case, the automatic air supply must be arranged to allow individual maintenance of air pressure for each separate dry pipe system. Each system needs its own dedicated air maintenance device, individual control for each system.
Yes. Furthermore, a check valve or other positive backflow prevention device is required in the air supply line to each individual system.
And that's to prevent air, or maybe even water if something went wrong, from one system from flowing back into the shared supply and affecting other systems, or air flowing between systems.
Exactly. It ensures the independence and integrity of each dry pipe system served by a common supply. You don't want one system's problems impacting another.
Good isolation. And if a compressor is the dedicated air supply,
Its electrical installation must comply with safety standards, specifically NFPA 70, the National Electrical Code, Article 430, which covers motors and compressors.
standard electrical safety. Now, how is the actual required system air pressure determined? How much pressure do you need?
It must be maintained either according to the dry pipe valve manufacturer's specific instruction sheet, they know their valve best,
Right.
or R, if that's not available or specified, it must be 20 psi above the calculated trip pressure of the valve.
Trip pressure, what's that?
The trip pressure is the minimum air pressure needed to hold back the highest normal water pressure, based on the dry pipe valve's specific design ratio, sometimes called its differential. Different valves have different ratios of air pressure needed per psi of water pressure.
Ah, so it depends on the valve design and the water pressure it's holding back.
Correct. So you need enough air pressure to meet that calculated trip point, plus a 20 psi safety buffer to keep the valve securely closed against the water pressure.
Okay, air pressure is critical. How is it monitored continuously?
Each dry pipe valve must have a low-high supervisory pressure switch. This device triggers a supervisory signal, not a full fire alarm, but a trouble signal if the air pressure goes outside the acceptable range.
What are the trigger points for low and high?
The low pressure signal is set at a minimum of 5 psi above the calculated trip pressure.
So it warns you before you actually hit the pressure where the valve might trip.
Exactly. It indicates that pressure is getting critically low. The high pressure signal is set at 5 psi above the normal system air pressure, signaling that pressure is potentially too high, which could stress components or maybe even slightly delay tripping, though the main concern is usually low pressure.
And these alarms need to be reported somewhere. You can't just have a light blinking on the valve.
No. These low or high pressure signals must notify building maintenance staff via an audible signal, or R. They must transmit a supervisory condition signal to the building's fire alarm control unit. This ensures personnel are alerted to investigate and rectify pressure issues before they compromise system operation.
Okay, ensure someone knows there's an issue. The source also mentions a permitted air leakage rate, referencing another section for the specific value. We don't need the number, but what's the point?
All right, Section 29.2.2 details the maximum acceptable rate of air leakage, which is a very low value. This ensures the system isn't losing pressure excessively. Constant significant leakage would cycle the air supply frequently and could indicate a problem like a loose fitting or a small crack somewhere in the piping.
Checking the system's tightness, basically.
Essentially, yes.
Now, about using nitrogen specifically, you mentioned it can be used instead of air. The source talks about using it for an increased C value in hydraulic calculations. What's that about?
Yes, this is a more advanced application. Nitrogen, being an inert gas, doesn't support oxidation, so it helps prevent or significantly reduce internal corrosion inside the steel pipes of a dry system.
Okay, less rust inside the pipe.
Right, less internal corrosion means smoother pipe walls. Smoother pipe walls result in lower friction loss when water eventually flows through them during a fire.
Ah, less friction loss.
Exactly. This is represented by a higher C value in the Hazen-Williams hydraulic calculation formula, which is commonly used for sprinkler systems.
So nitrogen's anti-corrosion property translates directly into a hydraulic benefit.
Precisely. A higher C value can mean you might be able to use smaller diameter pipes for the same flow, or run the pipes longer distances, while still meeting the required water flow and pressure at the sprinkler heads. It can make the hydraulic design more efficient.
That's a significant advantage. So if you want this benefit, how do you supply the nitrogen?
If nitrogen is used specifically for this purpose, to justify using that higher C's value in calculations, the supply must come from a listed nitrogen generator that is permanently installed.
So not just bringing in bottles of nitrogen periodically, it needs an on-site generator.
Correct. For this specific application aiming for the hydraulic benefit, it requires a listed generator. This generator must be capable of supplying and maintaining a minimum of 98% nitrogen concentration throughout the entire sprinkler system piping.
High purity is important.
Very. And it must be able to maintain this purity even if the system has a maximum air leakage rate of 1.5 psi per hour. So the generator has to keep up with minor leaks while maintaining purity.
That sounds demanding.
It is. And a means for verifying the nitrogen concentration in each system using this method is also required. You need to be able to check that you're actually getting the 98% purity. The generator itself must be installed and maintained according to the manufacturer's instructions and another chapter of the standard, Chapter 32.
So using nitrogen for corrosion benefits that impact hydraulic design comes with a specific set of requirements involving dedicated listed equipment and verification processes.
It does. It's a more sophisticated approach to system design and maintenance for dry pipe systems, often seen where corrosion is a major long-term concern or where hydraulic optimization is critical.
All right, moving on from dry systems, let's talk about pre-action and deluge systems. You mentioned these involve a detection system triggering the water flow before a sprinkler head might activate.
Correct. These systems add another layer of control before water enters the pipes. They're often used where accidental water discharge is a major concern. Think data centers, museums, archives.
Places where water damage would be catastrophic.
Exactly. Or they're used where a fire needs very rapid and widespread water application, which is more the territory of deluge systems. Pre-action is also common in cold storage freezers, as we'll discuss later, because it keeps water out until absolutely needed.
And deluge systems.
Deluge systems use open sprinkler heads, no heat-sensitive element. They're for high-hazard areas needing total flooding quickly, like aircraft hangars or chemical processing areas. When the detection system goes off, the valve opens, and water pours out of all the open heads at once.
Okay, the source covers general requirements applicable to both pre-action and deluge. What are some of those?
First, all components of the release system, whether they use pneumatic, air, hydraulic, water, or electrical signals, must be compatible with each other. Everything has to work together smoothly.
Makes sense.
The automatic water control valve for these systems, the pre-action or deluge valve itself, must have a manual means of operation, like a handle, pull station, something mechanical.
So you can trip the system manually if the automatic detection fails or isn't fast enough?
Yes, a crucial backup. Yeah. Also, a newer requirement, effective January 1st, 2021. If an electric actuator that controls the valve is removed, it must cause an audible and visual impairment signal at the control panel.
So you can't just disable the automatic operation without it being obvious.
Right. Prevents tampering or accidental disabling going unnoticed. Pressure gauges are required again above and below pre-action valves, just below deluge valves, and on the air supply line if one is used for supervision.
Standard procedure, checking pressure at key points.
Yep, monitoring system status. A supply of spare fusible elements, at least 2 of each temperature rating used in the system, must be kept on the premises.
For replacing activated detectors or sprinklers.
Exactly. Many pre-action deluge systems use heat-sensitive fusible elements, whether in the detectors themselves or, in the case of pre-action systems, the actual sprinklers, as part of the release mechanism. Having spares is essential for getting the system back online quickly after an event or during maintenance.
Makes sense for maintenance. For hydraulic release systems, ones triggered by water pressure in small tubes, there are height limitations.
Yes, if the release system is hydraulic, the installation must follow the manufacturer's requirements and listing for height limits of the release tubing above the main deluge valve or actuator.
Why the height limit?
It's to prevent issues potentially caused by the water column in that tubing. If the tubing goes too high, the weight of the water inside could create unintended pressure, potentially leading to false trips or interfering with proper operation.
Ah, the physics of water pressure in the trigger line itself. Okay. Location and spacing of the detection devices are critical since they trigger the whole system.
Absolutely. They must be installed according to their listing and the manufacturer's instructions, and they must cover all areas protected by the sprinkler system. And here's a key rule for systems triggered by thermal detection, like heat detectors or pilot sprinklers. The detection system's activation temperature must be lower than the activation temperature of the automatic sprinklers in that same area.
Lower temperature for the detector than the sprinkler head. Why is that critical?
Because in a pre-action system, the detection is the first step. It needs to sense the fire until the main valve to open, filling the pipes with water before the fire gets hot enough to actually open the sprinkler heads.
So the pipes are charged and ready when the sprinkler opens?
Exactly. By the time a sprinkler head fuses from the heat, the pipe should ideally already be full of water, allowing immediate discharge. If the detector activated at the same or a higher temperature, there'd be a delay while the pipes fill, or the system might not function as intended, effectively becoming a slower, dry pipe system at that point.
That's a clear engineering priority. Detection must lead the sprinkler activation for pre-action systems.
Precisely. For testing these detectors, if they are located in inaccessible places, like very high ceilings or tucked away inside equipment, an additional test device must be provided for each detection circuit in an accessible location. This test device must be connected in a way that ensures the entire circuit can be tested.
A remote test point.
Right. And the necessary apparatus for producing the heat or impulse needed to test the specific type of detectors used must be provided to the building owner. And importantly, in areas with potentially explosive vapors, testing methods that do not involve an open flame or spark, like using carefully applied hot water or steam, must be used.
Safety during testing is paramount, especially in hazardous environments. Good point. The source also mentions a separate valve specifically for maintenance testing.
Yes, this is a practical allowance. A supervised indicating control valve is permitted to be installed in the riser assembly above the main pre-action or deluge valve.
Above the main valve.
Yes. This valve, which should be supervised, closed during normal operation, allows maintenance personnel to perform full-function trip testing of the system, testing the detection, the valve trip mechanism, etc., as required by NFPA 25, the testing and maintenance standard, without actually discharging a huge volume of water into the entire system piping network.
Ah, so it isolates the main piping during a test trip, avoids flooding the system unnecessarily.
Exactly. It avoids a significant mess and the need for extensive draining and resetting afterwards. It's a practical addition for easier and less disruptive maintenance.
A bypass essentially for testing purposes. And like other critical valves, the control valves for pre-action and deluge systems must be protected from freezing and mechanical injury. Housed in heated and lighted rooms with a permanent heat source again, no heat tracing allowed.
Yes, that consistency in protecting vital components in cold areas runs throughout the standard.
Let's focus more closely on pre-action systems now and their different types. You mentioned three.
Right. Pre-action systems are defined by how they get water into the pipes, specifically the logic connecting detection and sprinkler operation. There are three main types specified.
Okay.
First is single interlock. In this type, water enters the piping network upon operation of the detection devices only.
So detector goes off, valve opens, pipes fill. Simple.
Simple logic, yes. One trigger of the detection system fills the pipes. Water won't discharge until a sprinkler head also opens due to heat.
Okay. What's next?
Second is non-interlock. Here, water enters the piping upon operation of either the detection devices or automatic sprinklers activating.
Either. So if a sprinkler head pops before the detector senses anything, the valve still opens.
Yes. Or if the detector goes off first, the valve opens. Either event triggers the valve, it provides a sort of backup if the detection fails, or is bypassed by a very rapidly growing fire that opens a sprinkler first, the system still activates.
Interesting. More redundancy there. And the third type?
Third is double interlock. In this type, water enters the piping only upon operation of both the detection devices and automatic sprinklers activating simultaneously.
Both have to happen. Detector and sprinkler activation.
Correct. Both conditions must be met to trip the main valve and allow water into the pipes.
So double interlock seems specifically designed to absolutely minimize the chance of accidental water discharge.
It is. Double interlock systems are the most common type used in those areas, highly sensitive to accidental water damage. We talk about museums, data centers, critical archives, and often in cold storage because they require two independent indications of a fire hot enough to activate detection and hot enough to open a sprinkler, before water is introduced into the piping. Much lower risk of a false discharge from, say, a damage detector or a physically damaged sprinkler head alone.
Makes sense. Highest level of protection against accidental water release. What about sizing these systems? How big can they be?
For single and non-interlock pre-action systems, the size limit is based on the number of sprinklers. Not more than 1,000 sprinklers can be controlled by a single pre-action valve.
Okay, just a simple sprinkler count limit for those two types. And double interlock, is it different?
Yes, double interlock sizing is more involved, much like dry pipe systems, because managing the time delay to water delivery is crucial even after the valve trips. System size can be determined by one of four options.
Four options again. Okay.
Option 1. A maximum system volume of 500 gallons is permitted, without requiring any specific water delivery time calculation or test, similar to the small dry pipe allowance.
Okay, volume-based.
Option 2. The system must be designed to deliver water to a test connection in no more than 60 seconds. This test is performed starting at normal air pressure, if used for supervision, and with both the detection system activated and the inspection test connection fully open simultaneously.
So you have to simulate both conditions happening at once for the test.
Right. Option 3. The size can be based on hydraulic calculations for water delivery, similar to the dry pipe calculation method, assuming simultaneous detection system activation and sprinkler operation.
Performance calculation again?
And option 4. The size can be designed to deliver water to a trick test connection or manifold outlets in no more than the maximum time allowed in that hazard table, table 8.2.3.6.1, again with both the detection system activated and the test connection or manifold open simultaneously.
So double interlock systems have either volume limits or performance-based timing requirements, often requiring testing or calculation, assuming simultaneous activation of detection and water delivery points, very similar to dry pipe sizing rules.
Yes, because even though the pipes might fill relatively quickly after detection in some designs, you still need that water to reach the fire rapidly once a sprinkler head actually opens. And just like with dry pipe systems, a listed quick opening device, QOD, is permitted to help meet the timed or calculated requirements for double interlock systems by speeding up the main valve trip when both conditions are met.
Got it. Supervision is also mentioned for pre-action systems with more than 20 sprinklers. What needs supervising?
If a pre-action system has more than 20 sprinklers, both the sprinkler piping network itself and the fire detection devices must be automatically supervised.
How do you supervise the piping if it's normally dry?
Usually with low-pressure air or nitrogen, typically around 7 psi or so for double and non-interlock systems. This supervisory pressure allows the system to detect leaks in the piping. A drop in this low pressure triggers a supervisory alarm before the main valve trips, signaling pipe damage or leak without causing an accidental water discharge.
So the air pressure isn't holding back water, it's just checking the pipes are intact.
Exactly. For non-interlock and double interlock systems, that's its primary purpose: integrity supervision. The detection system supervision ensures that detectors and wiring are operational. This combined supervision provides a warning of system impairment before a fire occurs.
Makes sense. Provides confidence the system is ready.
Precisely. For single interlock systems, the air pressure, if used, is set per the manufacturer's instructions, and that air supply relief valve required for dry pipes can sometimes be omitted. IF, the air source used for supervision, can't develop pressure above 15 psi.
Okay. And sprinkler types allowed on pre-action systems.
The permitted sprinkler types and arrangements are the same as specified for dry pipe systems. Upright, listed dry sprinklers, and pendant sidewall sprinklers only when installed on return bends in heated areas or using listed piping, copper CPVC, with potable water in areas kept above 40 degrees Fahrenheit.
So the same rules about preventing water trapping in cold areas apply if those sprinklers are on a pre-action system, even if the main system is protecting a sensitive area.
Exactly. The physics of freezing don't change. And one more configuration point. Double interlock systems, A&D, any pre-action systems protecting storage occupancies, except miscellaneous storage, are explicitly not permitted to be gridded. Same prohibition as dry pipe systems.
Keep it simple, no grids for these either.
Okay.
Finally, briefly on deluge systems, we touched on them.
Right. Deluge systems are simpler in concept in that they use open sprinklers, no heat-sensitive elements on the heads at all.
Just open nozzles.
Yes. When the fire detection system activates, the deluge valve opens, and water flows through all the sprinklers or nozzles on that system simultaneously. It literally deluges the entire protected area very quickly.
Total flooding.
Exactly. The source notes that their detection systems must be automatically supervised, just like pre-action, and the systems must be hydraulically calculated to ensure adequate flow and pressure can be delivered from every single open head at the same time.
Makes sense. If everything opens, you need massive flow, used for high-hazard areas needing immediate widespread application.
Precisely. Think aircraft hangars, chemical storage, anywhere you need to knock down a potentially fast-spreading fire over a large area instantly.
Now, a fascinating hybrid system mentioned in the source combined dry pipe and pre-action systems. The source ties this specifically to unique environments like piers, terminals, and wharves. Why there?
This system really combines features of both dry pipe and pre-action, and it seems tailored for these challenging marine or waterfront locations. Piers and wharves can be very large, exposed to freezing conditions, wind, cold air, maybe even spray, but also contain valuable goods or infrastructure, and fires can spread rapidly along them. So they need the cold protection of dry pipe, but also the potential for faster response and added reliability from combining detection with sprinkler activation.
Layering the protection for a tough environment, what's the core operating principle here?
Redundancy and fail safety seem paramount. The system must be designed so that a failure in the dry pipe sprinkler portion, like a broken pipe out on the pier exposed to cold, does not prevent the detection system from still functioning as an automatic fire alarm.
Okay, so even if the pipe breaks, you still get an alarm signal from the detectors.
Right. And conversely, a failure in the detection system does not prevent the system from operating as a conventional automatic dry pipe system, triggered solely by a sprinkler head activating due to heat.
So if the pipes break, you still get an alarm. If the detection fails, the sprinklers still work like a standard dry pipe system when they get hot enough. It's layered protection, belt, and suspenders.
Exactly. Really robust design philosophy for these critical infrastructure locations. A manual means to operate the detection system is also required at accessible locations, generally within 200 feet of travel distance.
Manual trigger capability.
Yes. Sprinkler types allowed are similar to standard dry pipe reaction. Upright, listed dry, pendant sidewall on return bends if heated, and also horizontal sidewall sprinklers are mentioned, likely because they also drain well and prevent trapped water.
The source details a really complex setup for the dry pipe valves in these systems, especially for larger ones. It sounds like overkill almost.
It's definitely robust. For systems with more than 600 sprinklers total, or more than 275 sprinklers in any single fire area, the entire system must be controlled by two 6-inch dry pipe valves installed in parallel, feeding into a common main pipe.
Two large 6-inch valves working together. That really emphasizes capacity and redundancy.
It absolutely does. These parallel valves must be checked against each other, meaning they work in concert. Each dry pipe valve has its own listed tripping device that's actuated by the fire detection system.
Okay.
The two valves are cross-connected using a 1-inch pipe. This cross-connection ensures they trip simultaneously when the detection system sends a signal.
So the detection signal effectively hits both valves at the same time via that small pipe connection.
Right. That 1-inch cross-connection must have an indicating valve in it, which allows one of the two main dry pipe valves to be isolated for maintenance while the other remains in service. This is vital for maintaining at least partial protection on these large critical systems during servicing.
Smart design for maintainability without complete shutdown. What about the check valves located downstream of these big dry pipe valves, between them and the common main pipe?
Another area with a very precise detail. These check valves must have 14-inch bypasses around them.
Quarter-inch bypasses, that's bigger than the 332-inch hole we heard about for subdivision check valves. Why bypass the check valve here? What's the purpose?
The standard explains this one. These bypasses are included so that minor air leakage from the valve, trimmings the small pipes and fittings around one of the main dry pipe valves, does not cause that single valve to trip prematurely.
Oh.
It allows the air pressure to equalize slowly between the valve chamber and the main feed pipe downstream. The valve only trips when the pressure in the main feed pipe drops significantly, which would happen when the other main valve trips, due to detection or sprinkler activation, or if there's a major pressure loss in the system itself.
So it prevents nuisance trips from minor leaks in the complex trim of just one of the parallel valves.
Yeah.
Very clever.
Yes, it enhances the system's stability. And naturally, an indicating valve is required in each of these 14-inch bypasses. This allows complete isolation of either dry valve from the main riser and the other dry valve for thorough maintenance or troubleshooting.
Essential for servicing these complex parallel valve setups. Quick opening devices, QODs, are also required at the dry pipe valves in these combined systems.
Yes. Given the potentially large system size and the critical need for rapid water delivery once detection occurs in these potentially large and hazardous pier or terminal environments, QODs are mandated to accelerate the trip time of the main dry valves.
Get water moving fast. Subdivision is also required if the system is large or covers multiple fire areas, similar to other systems.
Right. If there are more than 275 sprinklers in a single fire area, the system must be divided into sections of 275 sprinklers, or fewer, using check valves. If the system covers more than one fire area or story, no more than 600 sprinklers can be supplied through any single check valve.
Manageable sections. And each section needs draining capability.
Yes, a 114-inch drain is required on the system side of each check valve, plus a standard dry pipe auxiliary drain for low points. These drains must be located in heated areas or heated cabinets to prevent them from freezing, just like the main valve room.
Critical for maintenance in potentially very cold, exposed environments. What about the water delivery time requirement for these combined systems? Is it like dry pipe or pre-action?
It's a specific performance requirement tied directly to the detection system. Water must reach the farthest sprinkler within a time not exceeding 1 minute for each 400 feet of common feed main piping. This time is measured from the moment the heat-responsive detection system operates.
1 minute per 400 feet of main pipe, starting when the detector goes off, not when a sprinkler opens.
Correct. The clock starts when the detector sees fire, and there's an absolute maximum permitted time of 3 minutes, regardless of the pipe length.
That really emphasizes the role of the detection system in initiating the response quickly over potentially very long distances on a pier.
Yes, it reflects the design goal for these systems in environments where a fire might spread quickly along the structure and needs immediate large-scale water introduction as soon as it's detected.
The end section of these systems also has a system test connection, like standard dry pipe systems.
Correct, for verifying performance and doing trip tests.
Okay. Briefly, multi-cycle systems are mentioned in the source. What are those?
These are highly specialized systems. The key takeaway is that they must be specifically tested and listed as complete systems. They have to be installed exactly according to the manufacturer's specific instructions.
What do they do?
The basic concept is that they can cycle water flow on and off automatically in response to fire conditions. May be useful in scenarios where reignition is a high risk or where minimizing total water discharge is a factor after initial suppression has occurred. But the standard gives very little detail, basically saying they exist but require specific listing and adherence to manufacturer instructions, not a generic system type.
Got it. Specialized listed equipment. Okay, let's move to antifreeze systems. These are for protecting smaller, limited areas subject to freezing temperatures, typically connected back to a main water supply, maybe a wet pipe system.
Right. Instead of using complex dry or pre-action valves for just a small cold room or entryway, you can sometimes use an antifreeze system. The pipes in these small localized systems are filled with an antifreeze solution instead of plain water to prevent freezing.
Seems straightforward. What are the key requirements?
Firstly, and very importantly, the use of any antifreeze solution must comply with state and local health regulations. This is mainly about preventing contamination of the potable water supply.
Right, you don't want antifreeze getting back into the drinking water.
Absolutely not. A major technical restriction is that antifreeze solutions are not permitted in ESFR, early suppression fast response, sprinkler systems, unless the specific ESFR sprinkler head has been tested and is listed for use with that particular antifreeze solution.
We talked about ESFRs needing specific performance. Why the general prohibition with antifreeze?
ESFR sprinklers rely on a very specific high-momentum spray pattern to penetrate the fire plume and suppress challenging, high-piled storage fires quickly. The physical properties of an antifreeze solution, its viscosity, its density, how it atomizes when sprayed, could potentially alter that critical spray pattern. This could compromise the sprinkler's ability to suppress the fire effectively, as designed. So they need specific testing and listing together to prove compatibility.
That makes sense. Their performance is very sensitive to the fluid being sprayed. What about hydrostatic testing these antifreeze systems?
If pendant sprinklers are used in an antifreeze system sprinklers hanging down, then all the plain water used for the initial hydrostatic pressure testing must be drained completely from the entire system after testing is finished. That is, unless the hydrostatic testing was performed using a listed antifreeze solution instead of water in the first place.
Why is draining the plain water so critical, especially with pendant heads? It seems obvious you'd drain it. No.
You'd think, but it's critical to get all of it out. Pendant sprinklers, by design, have low points where small amounts of water can get trapped even after draining. If you hydrotest with plain water and then fill the system with antifreeze solution, any trapped pockets of plain water in the pendant heads or low spots in the piping will still freeze solid when the temperature drops, even if the surrounding liquid is antifreeze.
The pure water pockets will freeze inside the antifreeze.
Exactly. This can damage the sprinkler head or burst the pipe. Completely draining all the water, or better yet, testing with the actual listed antifreeze solution itself, prevents this risk.
Get every last drop of plain water out. Crucial detail.
Very. Placards are also required. One on the main system riser indicating how many remote antifreeze systems are supplied by that riser and where they are located.
So you know where these small systems are tapped in.
Right. And another placard right on the antifreeze system's main control valve. This one needs to state the manufacturer, the type and brand of the antifreeze solution used, its minimum rated use temperature, and the total volume of the solution in that specific system.
Important information for anyone maintaining the system, what's in it, how cold it's rated for, and how much they need if they have to refill it.
Definitely. Vital maintenance info. Regarding the solutions themselves, except for one specific exception, they must be listed for use in sprinkler systems by a recognized testing laboratory. You can't just pour car antifreeze in there.
Listed solutions only. What's the exception?
The exception is for pre-mixed propylene glycol. It's permitted for use with ESFR sprinklers if those specific ESFR sprinklers are listed for that application with that solution.
Ah, the ESFR exception again. If the sprinkler and the specific propylene glycol are tested and listed together, it's allowed.
Correct. It's a specific carve-out for that combination, if proven safe and effective through listing.
The standard gets into very specific piping and valve arrangements for antifreeze systems, often referencing figures, and it seems heavily focused on preventing backflow into the potable water supply.
Yes, absolutely. Preventing contamination of the municipal or building water supply is a major health and safety concern when you're connecting piping filled with chemicals like antifreeze to it. The specific arrangement of valves, check valves, and required backflow prevention devices depends on the setup, with different configurations outlined in figures in the standard.
And if a backflow preventer is used,
The setup must include a way to perform a full forward flow test of the backflow preventer itself, according to the testing standard, NFPA 25, or specifically 16.145 water referenced here, ensuring it's working correctly and not stuck or leaking.
makes sense. Test the safety device. If a backflow preventer is used, the source requires a listed expansion chamber. What's that for?
This is a crucial component whenever you have a check valve or backflow preventer creating a closed section of piping filled with liquid. Antifreeze solutions, just like water, expand significantly when they get warmer and contract when they get colder.
Thermal expansion and contraction.
Right. In a closed system, this thermal expansion can build dangerously high pressures, potentially damaging sprinklers or fittings. Contraction can create negative pressure or vacuum conditions. A listed expansion chamber acts as a buffer or accumulator. It contains a precharged air bubble, usually separated by a diaphragm or bladder, that compresses to absorb the expanding liquid volume when heated and expands to push liquid back out when cooled.
Like a shock absorber specifically for temperature-induced volume changes.
Precisely. It maintains relatively stable pressure within the antifreeze system despite temperature swings. The chamber must be sized correctly based on the total volume of the antifreeze system and the expected temperature range it will experience. It must be large enough to prevent the maximum system pressure from ever exceeding the lowest pressure rating of any component in that antifreeze system loop.
So the chamber size is specific to the installation, calculated based on volume and temperature delta. Is there an alternative to using an expansion chamber? They sound potentially bulky or expensive.
Yes, for small antifreeze systems only, specifically systems with a total volume of 40 gallons, about 150 liters or less. A simple half-inch pressure relief valve is permitted instead of an expansion chamber.
40 gallons is pretty small, like maybe just a small vestibule or loading dock alcove.
Exactly, it's for very limited volumes. For these smaller systems, a simple relief valve can adequately handle the pressure buildup from thermal expansion by just releasing a small amount of the antifreeze solution if the pressure gets too high. An expansion chamber is needed for larger systems where routinely releasing the solution isn't practical or desirable.
Okay, relief valve for small, expansion chamber for larger systems. Are there any other exceptions to these standard piping valve chamber requirements?
Yes, the standard notes that these specific rules don't apply. The system uses an alternative engineered approach. This involves using an automatic pressure pump or device that actively maintains a higher pressure on the antifreeze side of the system than on the water supply side.
Pushing back against the supply pressure.
Yes, and this active system must also include provisions for automatically releasing solution if needed for thermal expansion, A&E provisions for automatically supplying more premixed solution if needed due to thermal contraction. This describes a more complex active pressure maintenance system as an alternative to the passive components, like expansion chambers or relief valves.
An engineered active system instead of passive components. Okay.
Correct. A drain test connection is required at the most remote point of any antifreeze system. For larger systems, over 150 gallons, an additional test connection is needed for every additional 150 gallons of volume.
Why multiple test points on large systems?
This allows for easier draining of the system for solution replacement or maintenance, and also provides points to draw samples for testing the antifreeze solution concentration and condition over time.
Makes sense. And looking at those reference figures again, there's that small hole concept reappearing. A 132-inch, specified as 0.8 millimeter here, hole is shown in the clapper of the check valve where the antifreeze system connects back to the main water supply pipe.
Yes, another tiny hole. And the note in the standard explains this one very clearly. It's specifically to allow for expansion of the solution during a temperature rise, thus preventing damage to sprinklers.
So, this tiny hole allows the thermal expansion pressure of the antifreeze solution in that connecting piece of pipe between the supply valve and the check valve to push back ever so slightly against the supply pressure, bleeding off the expansion pressure, rather than letting that pressure build up in that small section and potentially damage the nearby sprinkler heads or fittings.
That seems to be exactly the intent. It's a very elegant, simple, passive solution to manage localized thermal expansion pressure in that specific, small, contained section of pipe right at the connection point. Another incredibly specific detail with a crucial purpose.
It's amazing how often these tiny engineered details appear. Moving outside the building now, let's look at outside sprinklers for protection against exposure fires. This isn't about fires inside the building, right?
Correct. This is about protecting a building from a fire happening next door or from some other nearby external fire hazard, like a wildfire approaching or a large fire in an adjacent structure. These are sprinkler systems installed deliberately on the exterior of a building.
A water shield, essentially.
Yes, the goal is to create a water curtain or thoroughly wet the building surfaces to protect against the intense heat radiating from that external fire. They can be used regardless of whether the building's interior has sprinklers or not.
What sorts of things do they protect on the outside?
They can be designed to protect specific vulnerable points like windows and other openings, especially in masonry walls which might otherwise resist fire well. They can also provide complete wall protection, protect combustible roofs, or any combination of these.
How are they supplied with water? Does it have to be the main building supply?
Generally, they can be supplied from a standard water supply that meets the requirements of Chapter 5, just like interior systems. However, the standard allows for approved alternative supplies, which might include things like manual valves connected to a reliable source, dedicated fire pumps, or even just fire department connections, FDCs.
FDCs. So the fire department hooks up and supplies the water.
Yes, if that's approved for this specific design and hazard. If FDCs are used as the primary supply, they must be located strategically so they won't be inaccessible or dangerous to use due to the exposing fire itself, which is just common sense. Firefighters need to be able to connect safely.
Right. Each system needs an independent control valve.
Yes, for isolation and control of each protected section or zone. Manually controlled open sprinklers, like deluge systems but manually operated, are only allowed if there's constant supervision present 24/7. You can't rely on someone hoping to be there to manually open the valve unless someone is always there and trained.
So usually automatic activation.
Usually, yes. The sprinklers themselves can be standard automatic, fusible link bulb, or they can be open nozzles activated by a separate fire detection system. If automatic sprinklers are used and located in areas subject to freezing temperatures, they must be protected appropriately using a dry pipe setup, an antifreeze solution, or by being listed dry barrel type sprinklers connected back to a heated wet pipe supply. That reinforces the theme. Freezing protection is needed wherever water-filled components are exposed to cold.
Got it. System components drains are needed, I assume.
Yes, a separate drain valve is required on the system side of each control valve, unless it's a simple top-fed open sprinkler system that naturally drains completely through the nozzles.
What about protecting corners of the building where an exposure fire might wrap around? How do you ensure coverage there?
Good question. If sprinklers are protecting two adjacent sides of a building from different potential exposure fires, and each side has its own separate control valve, the standard gives two options for the corner. One option is to connect the end lines of the two systems at the corner using check valves, arranged so that activating one system also operates one sprinkler just around the corner on the other system's piping. The intermediate pipe connecting the check valves must be arranged to drain properly.
A bit complex, linking the systems at the corner. What's the alternative?
The alternative is simpler. Just install an additional sprinkler on each system, located strategically right around the corner from the main line.
So either connect the systems with check valves and drains, or just add extra sprinkler coverage right at the corner to ensure there are no gaps in protection.
Exactly. Seems simpler to just add the extra head usually. And importantly, if a single exposure fire scenario could potentially affect two sides of the building simultaneously, the sprinkler system protecting those two sides must operate as a single system covering both sides. It should not be subdivided between the two affected sides.
Why is that?
To ensure adequate water flow and pressure is available across the entire area threatened by that single fire. Subdividing could potentially starve one side if the other activated first or required more flow.
Makes sense. Pipe and fittings used on the exterior must be corrosion resistant.
Obviously, yes. They're constantly exposed to weather, rain, sun, potentially salt spray in coastal areas, or industrial pollutants. Corrosion resistance is critical for longevity and reliability.
Strainers are required in the riser or feed main for sprinklers with K factors smaller than K2.8.
Yes, same reason as we saw in kitchen systems. Smaller K-factor sprinklers have smaller orifices, making them more prone to clogging from any small debris that might be in the water supply. Drainers protect these smaller openings.
Okay. A pressure gauge is required immediately below the control valve of each system. Standard practice.
Yes.
Sprinklers themselves, placement and coverage details seem quite specific for exterior use.
They are. A single horizontal line of sprinklers can protect a maximum of 2 stories of wall area or 2 levels of windows if the wall features are essentially flush, without significant projections.
What if there are projections like deep windowsills or architectural ledges?
If windowsills, cornices, or other architectural features create recesses or projections deeper than just 1 inch, then separate sprinklers are required for each window on each level affected by that projection.
1-inch projection triggers the need for dedicated sprinklers. That's incredibly precise.
Yes, it shows the concern that even small projections can effectively shield the area below them, like the window opening itself or the wall surface, from the water spray coming from sprinklers located higher up. You need direct application.
Okay. For general wall protection, where are sprinklers placed?
Typically located 6 to 12 inches horizontally away from the wall surface and vertically within 6 inches of the top of the wall section being protected. Maximum spacing along the wall is usually 8 feet, or as per the sprinkler's listing. This placement ensures the water effectively wets and cools the wall surface as it flows down.
And for window protection specifically?
Listed window sprinklers are used, and they must be positioned very precisely, typically within 2 inches of the top of the window sash, according to a table in the standard, Table 8.7.8.4. This table gives specific distances the sprinkler should be located horizontally from the window opening based on the window's width and the sprinkler's K-factor, mentioning K-factors like 2.8, 5.6, 11.2. These positions are optimized through testing to ensure the water spray effectively covers the entire window glass area.
Tailored placement and specific K-factors just for protecting windows. It's not one size fits all.
Definitely not. For combustible cornices that project more than 12 inches, listed cornice sprinklers are required. They're installed within the bays of the cornice with a maximum 10-foot spacing, and their deflectors positioned about 8 inches below the roof, sheathing above.
Protecting that overhang. What about roof protection?
For roof protection, standard open spray sprinklers, upright, pendant, or sidewall types, are allowed. They are generally installed following the criteria for ordinary hazard group 1 occupancies, with deflectors positioned parallel to the roof slope and about 18 inches above the roof surface. Upright sprinklers located right at the ridge pole of a peaked roof, with horizontal deflectors positioned 6 inches above the ridge, are also permitted, with their spacing and coverage area determined in plan view.
All about getting water onto that exterior surface effectively, whether it's a vertical wall, a window, a cornice, or a sloped or flat roof.
Exactly. And the hydraulic calculation for these outside systems is different from interior systems. It's based on the severity of the expected exposure fire, which is often categorized or indicated by a guide number from related standards or calculations. Minimum discharge pressure from any sprinkler can't be below 7 psi.
Okay. And there's a key point about calculating the flow needed.
Yes. When calculating the minimum average application rate of water needed over the protected surface, like GPM per square foot, only half of the nominal flow rate from non-directional sprinklers, like standard upright or pendant spray sprinklers, is actually considered effective and used in the calculation.
Only half the sprinkler's flow counts towards the application rate on the surface. Why is that? Seems like you're discounting half the water.
It seems counterintuitive, but think about it. For protecting a vertical wall or even a sloped roof, you need the water to actually impinge on the surface, wet it, and flow down it to provide cooling and create a protective barrier. A standard upright or pendant sprinkler sprays water outwards in a roughly circular or hemispherical pattern. Not all of that water effectively contributes to wetting the vertical wall or sloped roof surface directly below or adjacent to it. Some sprays past, some might evaporate quickly in the intense heat. The standard accounts for this inefficiency in surface wetting by only using half of the sprinkler's nominal flow rate in the calculation for the required application rate on the surface itself.
Interesting. So the standard adjusts the calculation based on how effectively the water from that type of sprinkler is likely to be applied to the specific surface type being protected. That's sophisticated.
It is. The table referenced, Table 8.7.9.1, provides these required minimum average application rates in GPM FTIN, or AUGMIN, based on the exposure severity, light, moderate, severe, often linked to guide number ranges, and for different levels of wall window protection, for example, top 2 stories, next lower 2 stories, using various sprinkler K factors.
So the design goal is clear. Achieve a specific density of water application on the exterior surface being protected, and that density is matched to the expected severity of the fire next door. The table also provides application rates per lineal foot for those special cornice sprinklers.
Exactly. It's all about surface wetting performance.
The water supply capacity and duration required for these outside exposure protection systems seem quite robust.
They are. The water supply must be capable of handling the total calculated water demand along any continuous 300-foot length of the building's exposure section. If open sprinklers are used, like a deluge configuration, the supply must be able to handle all the sprinklers that would flow simultaneously in any 300-foot length along that exposure.
A 300-foot section is a lot of sprinklers, potentially.
It can be. And the minimum required duration for the water supply is a substantial 60 minutes, 1 full hour.
An entire hour of continuous water flow just for outside exposure protection? Wow. Why so long?
Because exposure fires, especially large building fires or wildfires, can burn intensely for extended periods, sometimes for hours. A 60-minute water supply duration ensures the system can maintain that protective water barrier on the building exterior for a prolonged event, significantly increasing the chances that the protected building will survive the exposure without igniting itself. It buys valuable time.
That makes sense. A long duration for a long duration threat. And for window sprinklers specifically, the source clarifies. A level of window sprinklers means one floor level. They can cover window areas larger than 25 square feet. And the starting pressure calculation for design is based on achieving the required application rate over that nominal 25 square foot area per sprinkler. Maximum spacing is typically 8 feet unless they're listed for more.
Right, again, emphasizing the focus on delivering a specific density of water, application rate, over the window, opening itself to counter the radiant heat passing through.
Now let's really focus on the environment we mentioned right at the start, which presents perhaps the most unique challenges for water-based systems. Refrigerated spaces. This is where the ambient temperature is constantly below freezing.
Yes, protecting areas maintained below 32 degrees C, commercial freezers, cold storage warehouses, is arguably one of the trickiest applications for water-based fire sprinkler systems. The constant primary risk is that any moisture or water that manages to get into the cold piping section will freeze solid and form an ice plug, completely blocking the pipe and rendering that part of the system useless in a fire.
A frozen pipe is no pipe at all when you need water.
Exactly. So almost all the specific design and installation rules in this section of NFPA 13 are aimed squarely at preventing water or excessive moisture from getting into the cold pipes until a fire actually happens, and ensuring the system can still function reliably if it does.
It's all about managing water and ice. What's one of the first specific requirements mentioned?
A really critical one concerns where the sprinkler piping passes through a wall or floor from a warm area like a heated corridor or a valve room directly into the refrigerated space. Right there, immediately inside the cold space, the standard requires a section of pipe to be installed that is specifically arranged for removal.
Arranged for removal, like a spool piece or union connection. How long does this section need to be?
It has to be a minimum 30 inches long. The reason for this removable section is simple but absolutely vital. It's there purely to facilitate inspection and, if necessary, the easy removal of ice plugs if they happen to form right at or near that critical transition point from the warm area to the cold area.
Why is that point so critical for ice plugs?
Because even with dry air supplies and careful installation, some moisture might still condense or freeze right at the point where the relatively warm pipe first enters the deeply cold freezer environment. It's a likely spot for initial ice formation. This removable 30-inch section allows maintenance personnel to easily take out that piece, visually inspect inside, and physically clear any blockage without having to cut pipes or perform major dismantling inside the freezing cold space.
That's a very practical requirement addressing a specific, predictable point of failure or blockage. Smart.
It is. Very pragmatic. Another requirement is for a low air pressure alarm, connected to signal a constantly attended location.
To warn if the supervisory air pressure drops.
Right. Detecting even small air leaks in the dry piping quickly is crucial before they allow significant air loss, which could potentially draw moist air into the system, or, in a pre-action system, risk a valve trip. However, this constantly attended alarm isn't necessary if the system already has local low-pressure alarms right at the valve, and it's served by an automatic air maintenance device that keeps the pressure topped up.
Okay, redundancy in alarming or automatic maintenance can satisfy the need. Piping pitch is also critical here, I assume, even more so than standard dry pipe.
Absolutely essential. All piping within refrigerated spaces must be installed with proper pitch, specifically following the requirements laid out in another section of the standard, 16.0.3.3, which details minimum slopes for drainage. This pitch ensures that any condensation that might form inside the pipes despite dry air, or any tiny amounts of water that might accidentally enter during testing, or a minor valve weep, will reliably drain completely back towards the main dry pipe or pre-action valve located back in the heated area.
Every single degree of pitch matters to get every last potential drop of moisture out of those cold pipes.
Yes, preventing any moisture from pooling or getting trapped in the cold pipes is fundamental to preventing ice plug.
Makes perfect sense.
And the air or nitrogen supply used for systems in refrigerated spaces has special rules aimed at providing the driest possible air or gas into those cold pipes, going beyond standard dry pipe requirements.
What are the options for this super dry air?
The permitted options are 1. Drawing the intake air for the compressor directly from the room of the lowest temperature within the facility because colder air inherently holds less moisture.
Yeah.
2. Using a specifically listed air compressor that comes as a packaged unit with an integrated air dryer designed for this application. 3. Using compressed nitrogen gas supplied from cylinders instead of compressed air nitrogen is inherently very dry.
So the engineering priority is crystal clear. Introduce as little water vapor into the cold pipes as humanly possible right from the start.
Precisely. Minimize the moisture source. Another practical rule. The main control valve used for operational testing of a refrigerated space sprinkler system must be an indicating type valve located on each sprinkler riser outside of the refrigerated space.
Test valve in the warm area.
Yes. This allows maintenance personnel to perform necessary system tests like trip tests or flow tests from the relative comfort and safety of the warm area, without having to enter the freezing environment unnecessarily just to operate a critical test valve.
That makes a lot of sense for practicality and worker safety, less time spent in sub-zero conditions. The source also notes a check valve, often installed in the system riser, below that test valve, frequently has that familiar small hole in its clapper.
Yes, here we go again. Generally a check valve with a 332-inch, here specified parenthetically as 2 mm diameter hole drilled in the clapper, is required in the system riser, located below the main test valve.
Another small hole, slightly different size, maybe 2 millimeters, 3 millimeters, 0.8 millimeter elsewhere. Why is it needed here, in the riser below the test valve in a freezer system?
The standard doesn't give an explicit explanation for the purpose of this specific hole in this location, unlike the antifreeze check valve hole note. However, considering its location in a refrigerated system riser and the pattern we've seen with holes in other check valves, like the dry pipe subdivision check valves allowing pressure equalization, or the antifreeze check valve allowing thermal expansion bleed-off, it's highly likely related to managing pressure differentials or allowing very slow drainage or expansion-contraction accommodation. It could potentially help equalize pressure across the check valve during temperature fluctuations, or allow minuscule amounts of condensation or residual test water trapped below the main test valve to pass through very slowly without causing a significant problem or ice buildup.
Interesting that the size is specified slightly differently here, 2 millimeter compared to the 3 millimeter for dry pipe subdivision or 0.8 millimeter for antifreeze. It really suggests careful fine-tuning of these small details based on the specific application and the perceived risk or need in each case.
It certainly seems that way. There is an exception provided for needing this check valve with a hole. It's not required if you're using specific types of dry pipe or pre-action valves that are listed for installation without needing any priming water, and they are designed to completely drain all water from above their seat after operation.
Ah,
A and D, crucially, no priming water is actually used in the field installation.
So, if the main system valve itself inherently prevents water from being trapped above it and doesn't need priming water, then the check valve with the hole below the test valve isn't necessary.
Correct. The valve design itself mitigates the potential issue that the check valve with the hole is likely intended to address.
Okay, let's look closer now at the actual air or nitrogen supply piping as it enters the freezer area from the warm space. This section in the source is quite specific and even references figures.
It is very specific, focusing on that critical warm-to-cold transition again. For an air supply, coming from a compressor entering the freezer, the supply piping arrangement must include TWO easily removable supply lines.
Two parallel lines for the air supply.
Yes. These lines must each be at least 6 feet long and a minimum of 1 inch in diameter. Both lines must have their isolation control valves located back in the warm area outside the freezer. And critically, only one of these two air supply lines is allowed to be open and feeding the system at any given time.
Two lines installed, but only one is ever in use. Why the mandatory redundancy just for the air supply connection?
The standard doesn't explicitly state the reasoning for requiring two airlines versus only one for nitrogen. Nitrogen supply only requires one easily removable line, also minimum 6 foot long, 1 inch diameter, with its valve in the warm area. However, a likely reason is reliability. Air supply typically comes from a mechanical air compressor system, which is subject to maintenance needs or potential breakdown. Having a fully installed, redundant parallel supply line with its own valve back in the warm area allows maintenance staff to simply switch over to the standby line if the primary line or the connection filter right at the freezer entry needs inspection, clearing of potential ice condensation, or repair, ensuring the sprinkler system can continue to maintain its crucial supervisory air pressure without interruption.
So it's likely about maintaining continuous air supply during maintenance of the connection point itself, which might be prone to issues.
That seems the most logical reason for the mandated parallel airlines. Nitrogen supplied from cylinders is typically just a matter of swapping tanks when one runs low, perhaps making a single robust connection line deemed sufficient. The easily removable aspect of the lines themselves, likely via unions or flanges, is also key again, facilitating inspection or clearing of any ice or condensation that might form right at the freezer entry point, despite all the other precautions like dry air.
That redundancy for the air supply connection makes sense, especially if it's coming from a mechanical compressor system. The figures referenced in the source presumably show these specific arrangements visually illustrating the control valves safely located back in the heated area, and these required removable pipe sections situated just inside the cold space.
Yes, exactly. These are critical physical design elements, specifically intended to protect against ice plugs forming right at that challenging warm-to-cold transition point, and to ensure the vital air or nitrogen supply remains functional at all times.
Finally, for refrigerated spaces, the requirements for fire detection used for pre-action system release get very detailed. This seems like a critical area.
Absolutely. For pre-action systems installed in freezers, which are common precisely because they keep water out until detection confirms a fire, the detection system that trips the main pre-action valve must normally be designed to operate prior to any of the automatic sprinkler heads activating from heat.
Detection first, just like standard pre-action, how is that achieved in a freezer?
Typically, this means using either electric or pneumatic fixed temperature type heat detectors. And critically, these detectors must have temperature activation ratings that are lower than the activation temperature rating of the sprinklers being used in that same area. Rate of rise type heat detectors are generally not permitted for primary release in these applications.
So fixed temperature detectors set to trigger at a lower temperature than the sprinklers to ensure detection happens first. And why no rate of rise detectors? Is it because temperature changes in a freezing environment during defrost cycles or door openings might cause false activations?
That's the likely reason, yes. Freezer temperatures can fluctuate, and rate of rise detectors might be prone to nuisance alarms. You want reliable detection based on reaching a specific, fixed temperature threshold that indicates a real fire, and that threshold needs to be below the sprinkler's activation point to get the pipes filling first.
Makes sense. But there's a significant exception mentioned.
Yes, this strict requirement for detection being faster than sprinklers is waived under certain conditions. Specifically, for double interlock pre-action systems, or R, for single interlock pre-action systems that use an antifreeze solution in the piping, the detectors are permitted to be any type that is specifically listed for use in refrigerated areas, provided they are installed according to their listing and the relevant fire alarm standards, like NFPA 72.
So if you already have the extra protection against accidental discharge provided by a double interlock system, or if the pipes are filled with antifreeze, meaning immediate water delivery isn't the only goal upon valve trip, then standard detectors listed for cold environments are acceptable, even if they might not strictly activate before a sprinkler potentially could in a very fast fire.
Exactly. The system's inherent design, double interlock needing both detector and sprinkler,
Yeah.
or the medium being used, antifreeze already in the pipes, changes the risk profile and modifies the requirements for the detection speed relative to sprinkler activation.
Interesting interaction between system type and detector requirements. Detector location is also specified in detail, particularly when sprinklers are installed within storage racks, which is common in warehouses.
Yes, under smooth ceilings in the freezer, standard listed spacing for the detectors applies. Under other ceiling types, like open joists, the detector spacing is limited typically to half the listed linear spacing or the full allowable sprinkler spacing, whichever is greater, similar to obstruction rules for sprinklers themselves. Within storage racks, the general rule is that one level of heat detectors is needed for each level of in-rack sprinklers, unless a specific exception for ceiling-only detection is met.
So, detectors need to be distributed vertically throughout the rack structure, alongside the in-rack sprinklers, to catch a fire starting deep within the storage.
Yes, that's the intent. They are typically placed vertically within one storage level of the corresponding rack sprinklers. Specific locations are often recommended or required in the flue spaces, the open vertical channels within the racks. Usually the transverse flue, side-to-side, in single-row racks, or the longitudinal flue, down the aisle direction, in double-row racks.
Why the flue spaces?
Because that's where heat and smoke from a fire originating within the racks are most likely to travel upwards quickly, allowing for faster detection. For multiple row racks, which might not have a clear longitudinal flue, detectors can be in either flue space, but must be located within 5 feet horizontally of each sprinkler they are associated with.
Very close placement to ensure rapid detection of a fire starting right there amongst the dense storage.
Exactly. Separate detection systems, separate zones or circuits on the fire alarm panel, are typically required for the ceiling level sprinklers and the in-rack sprinklers. However, there's an exception here too. For double interlock pre-action systems, the ceiling detection system shall be permitted, and often designed, to operate the solenoid release valves on both the ceiling pre-action system and the in-rack pre-action systems simultaneously.
So, in a double interlock freezer setup, the ceiling detection confirming a fire can be used to release water into both the ceiling and the in-rack piping systems at the same time. Streamlines the control logic.
Yes, it simplifies the release activation for that specific system type. And there's one more major exception regarding detection location. It allows using only ceiling level detection, no in-rack detectors needed, for activating both ceiling and in-rack sprinklers. IF. All of a specific set of conditions are met.
All conditions must be met. What are they?
It's quite restrictive. Ceiling detection only is permitted by F. 1. Maximum storage height is 35 feet or less. 2. Maximum ceiling height is 40 feet or less. 3. The commodity hazard is Class 3 or lower, less challenging fuels. 4. There are NO solid shells used within the racks, only open grating or wire mesh. 5. And single pre-action valve is used to supply both the ceiling and the in-rack sprinklers protecting the same area. But duty, this shared valve must have separate indicating control valves and check valves installed downstream to individually control the feed to the ceiling portion and the feed to the in-rack portion. A specific valve arrangement shown in Figure 8.8.2.4. Yeah.
Wow, that's a very specific combination of factors. Lower storage height, lower ceiling height, lower fire hazard commodity, no solid shells to block vertical fire spread, and a specific shared valve arrangement with separate downstream controls. If you meet all of those, you can simplify the detection layout by omitting the in-rack detectors.
Exactly. It highlights how the standard carefully balances risk reduction, need for in-rack detection in most cases, with practical installation cost complexity based on a specific lower-risk storage configuration. That figure reference clearly illustrates the required downstream valve setup for this exception.
It's a complex but incredibly meticulously detailed approach, all tailored to the unique and severe challenges of providing reliable fire protection in constantly freezing environments, ensuring detection and water delivery happen when needed while doing everything possible to prevent accidental discharge or ice blockage.
Absolutely. It's arguably one of the most challenging environments requiring the most detailed consideration in the standard.
Let's completely shift gears now to a very different but equally specific and challenging hazard: commercial type cooking equipment and the associated ventilation systems. We're talking restaurant kitchens and grease fires.
Yes, another distinct and high-risk fire hazard area. The standard requires that in cooking areas already protected by general automatic sprinklers, meaning there are standard overhead sprinklers installed in the room, additional, specifically targeted sprinklers or automatic spray nozzles are needed to protect the commercial cooking equipment itself, like fryers, griddles, broilers, and the associated ventilation systems, the hoods and ducts that carry grease-laden vapors. This additional protection is necessary, unless that equipment and ventilation system are already protected by another approved method, typically a listed dedicated fire extinguishing system.
So the standard room sprinklers overhead aren't considered sufficient on their own to handle a potential grease fire erupting on the cooking line or inside the hood and ducts.
Not on their own, no. Grease fires are intense, can spread rapidly into the exhaust system, and need suppression applied directly at the source. So you need dedicated protection, specifically targeted at the areas where grease accumulates and fires are most likely to originate and spread. Inside the exhaust ducts, at the hood exhaust duct collars, where the hood connects to the duct, and within the hood exhaust plenum chambers, the space inside the hood above the filters.
Okay, target those specific hot spots.
Right. And additional sprinklers or nozzles are also needed to protect the cooking equipment surfaces themselves. Unless I mentioned, the hoods covering that equipment already contain a listed fire extinguishing system. These are typically wet chemical systems designed specifically for kitchen hazards, often meeting UL 300 standards.
Ah, okay. So if the hood itself has its own built-in listed suppression system, like those nozzles you see under hoods, then that system is considered to protect the equipment under the hood, and you don't necessarily need additional sprinklers from the building system spraying directly onto that equipment.
Correct. NFPA 13 clarifies this interaction. It notes that hoods containing listed fire extinguishing systems are considered protected areas. They don't count as obstructions to the general overhead room sprinklers, and you don't need specific floor coverage from the overhead sprinklers underneath these protected hoods. Furthermore, the cooking equipment located directly under these properly protected hoods does not require additional dedicated protection from the general building overhead sprinkler system.
That's an important clarification. It explains how the building sprinkler system, NFPA 13, interfaces with the dedicated kitchen hood suppression systems, often governed by standards like NFPA 96 and UL 300. Where are the sprinklers or nozzles located within the exhaust ducts themselves?
The general rule is one sprinkler or nozzle is required at the top of each vertical riser in the ductwork and also at the midpoint of each significant offset change in direction in the duct.
Protecting the high points and turns where grease might accumulate or flow could be restricted.
Exactly. However, there are exceptions. Sprinklers aren't needed in vertical risers located outside the building if that riser doesn't expose any combustible building materials, or if the horizontal distance inside the building between the hood outlet and the start of the vertical riser is at least 25 feet, allowing grease to potentially cool or deposit before the riser. For horizontal duct runs, sprinklers or nozzles are required on 10-foot centers, starting no more than 5 feet from the duct entrance.
Every 10 feet along the horizontal runs, that provides coverage down the line. Any exceptions for horizontal ducts?
Yes, sprinklers or nozzles aren't required in the horizontal ducts. IF, the total length of those horizontal ducts is 75 feet or less A&D. The entire exhaust duct system is protected according to the requirements of NFPA 96.
So if you meet the protection requirements of NFPA 96, which covers ventilation control and fire protection for commercial cooking, you might not need sprinklers inside shorter ducts per NFPA 13, interplay between standards again.
Yes, NFPA 96 is the primary standard for kitchen exhaust systems. NFPA 13 provides the sprinkler requirements when sprinklers are used as part of that protection. The source also reminds us, logically, that any sprinklers or nozzles located in ducts that might pass through unheated areas, like an attic or outside wall, and are subject to freezing temperatures must be protected against freezing, for example, using dry pendant sprinklers.
Makes sense. Even in a generally hot kitchen duct, parts of it could be exposed to cold. What about right where the hood connects to the duct, the collar?
A sprinkler or automatic spray nozzle is required at each hood exhaust duct collar. It must be located very precisely, between 1 inch minimum and 12 inches maximum vertically above the point where the duct collar connects into the hood plenum chamber.
A very specific location window. Why there?
That transition point is a prime area for grease buildup and potential fire ignition or spread into the duct. Placing a nozzle there targets this critical zone effectively. If the hood design includes a listed fire damper installed right in the collar, then the sprinkler or nozzle must be located on the discharge side downstream of that damper and positioned so it won't physically interfere with the damper closing properly.
Okay, protect the duct just downstream of the fire damper if one exists, and the plenum chambers themselves inside the hood.
The plenum chamber, that open space inside the hood, usually above the filters where vapors collect before entering the duct, also needs protection. One sprinkler or nozzle is required, located centered, in plenum chambers that are 10 feet long or less. For chambers longer than 10 feet, two sprinklers nozzles are required, evenly spaced, with a maximum distance of 10 feet between them.
Targeting that main collection area for grease-laden vapors right inside the hood makes sense. What about temperature ratings and K factors for these kitchen protection sprinklers nozzles? It must get incredibly hot in those hoods and dooks.
It certainly does. The standard requires that where the normally anticipated temperature exposure during cooking operations is 300 degrees F, about 150 degrees or less, the sprinklers or nozzles used in the duct, collar, and plenum areas must have an extra high temperature classification. These are typically rated to activate somewhere between 325 degrees air and 375 degrees air, which is 163 degrees C to 191 degrees C.
Extra high temp is the minimum starting point. What if it gets even hotter?
If temperature monitoring or assessment indicates that ambient temperatures during operation regularly exceed 300 degrees air, then an even higher temperature classification sprinkler or nozzle, like very extra high or ultra high, is required. For K factors, which relates to orifice size and flow, the standard requires a minimum K 1.4 and a maximum K 5.6 for sprinklers nozzles used in these specific duct, collar, and plenum locations.
So very high temp ratings are standard, and K factors are generally on the smaller side, likely designed for the specific flow needed to coat surfaces or fill these confined spaces effectively.
Yes, tailored for the hazard. Access is also a requirement. Adequate access must be provided to all sprinklers and nozzles installed in these hood and duct locations to allow for periodic examination and replacement if needed.
Makes sense. You need to be able to get to them to inspect and maintain them, especially in a greasy environment. Protecting the actual cooking equipment itself, like deep fat fryers, is specifically mentioned.
Right. General ignition sources like standard fryers, ranges, griddles, and broilers are covered by the main requirement for protection, either by sprinklers nozzles or a listed hood system. However, for deep fat fryers specifically, the standard states that the sprinkler or automatic spray nozzle used to protect them must be listed specifically for that application. Its positioning, arrangement, location, and the water supply characteristics, pressure, flow, must be strictly in accordance with that specific listing.
A special listing just for protecting deep fat fryers. Why the extra requirement there?
Because fires involving large quantities of hot cooking oil or grease are unique and particularly hazardous. They have high fuel loads, potential for auto ignition, violent flare-ups, and the risk of splashing burning oil if water is applied improperly. Sprinklers or nozzles listed specifically for deep fat fryer protection have undergone rigorous testing to prove they can effectively control and suppress fires in this very challenging fuel type without causing dangerous splashing.
Okay, specialized testing for a specialized hazard. And now, perhaps the single most critical safety feature required in this whole cooking protection section.
Absolutely. It's the mandatory automatic fuel and heat shutoff. This is a non-negotiable requirement. The operation of any cooking equipment sprinkler or automatic spray nozzle, whether for equipment, hood, or duct protection, must automatically shut off all sources of fuel and heat to all the cooking equipment that requires protection under that specific ventilation system.
All fuel, all heat to all protected equipment under that hood shuts off automatically when any part of the system activates.
Yes. And furthermore, any other gas appliances that might be located under the same ventilation hood but perhaps didn't require dedicated protection must also be automatically shut off. Critically, all these fuel and heat shutdown devices, valves for gas, contactors for electricity, most require manual resetting. They cannot automatically restore power or fuel flow after the fire event.
So one sprinkler head goes off over a fryer, and it instantly cuts the gas and or electricity to everything it's supposed to protect under that hood and maybe even other gas appliances nearby. And someone physically has to go and flip a switch or turn a valve back on to restart anything after the fire department leaves.
Precisely. The fire safety logic here is clear and paramount. In a grease fire, removing the heat source and the fuel supply is the most critical step to prevent reignition and control the fire. Manual resetting ensures that qualified personnel assess the situation, ensure the fire is out and the cause rectified, and confirm it's safe before any cooking equipment can be started up again. It prevents restarting equipment into a still hazardous situation.
A listed indicating valve is also required in the water supply line that's dedicated solely to these cooking equipment and ventilation sprinklers nozzles.
Yes, allows this specialized subsystem to be isolated for maintenance without shutting down the main building sprinklers. And just like other systems using sprinklers with small orifices, a listed line strainer is required in the supply pipe upstream of any sprinklers or nozzles having K-factors smaller than K2.8 to prevent potential clogging from waterborne debris.
And finally, a test connection is required somewhere in the system specifically to allow verification of the proper operation of that absolutely vital fuel and heat shutoff equipment.
Yes, that critical shutdown function must be periodically tested to ensure it works reliably when called upon. You have to know that interlock is functional.
Absolutely. Okay, let's wrap up our journey through these specialized systems with a look at pilot line detectors. These are often the initiating devices, the sensors, used to activate deluge or pre-action systems.
Correct. Pilot line detectors are essentially the heat-sensitive triggers that tell a deluge or pre-action valve it's time to operate. The standard has some general requirements for them. If they're installed outdoors or in corrosive environments, they and their associated components must naturally be corrosion resistant. They also need to be protected against potential mechanical or physical damage.
Makes sense, protect the trigger. The source notes, interestingly, that standard spray sprinklers, the same kind used for discharging water, can actually be used as pilot line detectors.
Yes, that's quite common. A standard fusible link or glass bulb spray sprinkler head can function perfectly well as the heat-sensitive element in a pilot line. When used this way, they are installed according to the rules in this section, 8.10, and the general sprinkler spacing rules regarding distance between them from section 10.2. The rules regarding obstruction to water distribution that normally apply to automatic sprinklers do not apply when they're used as pilot detectors.
Because their job here is just to detect heat and activate the release system, not to actually distribute water effectively.
Exactly. Their sole function in this role is to sense the heat, fuse, or break the bulb, which then triggers the release system, whether it's pneumatic, hydraulic, or electric. How the deflector might distribute water is completely irrelevant for this purpose. If they are installed under a ceiling, however, their positioning relative to the ceiling still follows the standard requirements from 10.2 to ensure they sense the heat collecting there properly.
Okay. The temperature rating of these pilot sprinklers detectors is selected based on the environment, just like regular sprinklers.
Yes, the temperature rating is selected according to the criteria in section 9.4.2, which generally requires choosing a rating based on the maximum expected ambient ceiling temperatures in the protected area, ensuring they don't activate prematurely, but do activate reliably when a fire occurs.
What about the maximum horizontal spacing allowed between these pilot detectors?
For indoor locations, the maximum horizontal spacing permitted between pilot line detectors is generally 12 feet. There's a note that they can be spaced more than 22 inches down below a ceiling or deck mantel. The maximum horizontal spacing used is reduced to 10 feet or less. Other spacing might be permitted if the specific detector is listed for wider spacing.
Okay, 12 feet max indoors, typically. What about outdoors? I imagine wind and weather affect how heat travels, requiring closer spacing.
Yes, outdoor conditions are considered less predictable for heat collection. The maximum horizontal distance permitted between pilot line detectors installed outdoors is a stricter 8 feet.
8 feet max outdoors. Can that ever be increased?
Yes, it can be increased slightly up to 10 feet outdoors, but only if a specific set of conditions are met. 1. The elevation of the first lowest level of detectors is 15 feet or less above the hazard. 2. The vertical distance between any additional levels of detectors above the first is 12 feet or less, A and D3. The pilot line actuator, the detectors themselves, are staggered vertically from level to level.
So, closer 8 foot spacing is the default outdoors. Relaxed slightly to 10 feet only under specific geometric criteria regarding height and vertical staggering. Seems conservative.
It is, reflecting the uncertainties of outdoor heat detection. Alternate vertical spacing arrangements outdoors are also permitted if based on the detector's specific listing.
What about open-sided buildings like a pavilion or a structure with one or more walls missing?
For open-sided buildings, they generally follow the indoor spacing rules for the interior portions. But T, a row of detectors spaced according to the stricter outdoor rules, 8 foot max or 10 feet with conditions, is required along each of the open sides.
A blend of indoor and outdoor rules for partially enclosed structures. Makes sense.
Yes. And interestingly, pilot line detectors located underneath open gratings, like walkways or mezzanines made of grating, must also follow the outdoor spacing rules.
Why under gratings? Seems like it would be somewhat sheltered.
It's likely because open gratings allow significant airflow through them, potentially mimicking the drafty, less predictable heat collection conditions similar to truly outdoor locations, thus warranting the tighter outdoor spacing rules.
Okay. If you have multiple adjacent systems in one large area, each using its own separate pilot line detection system.
If two or more adjacent water spray or deluge systems within the same fire area use separate pilot line detection systems to activate them, the detectors on each system must be spaced independently, calculated as if a physical wall or draft curtain existed between the systems.
So you don't accidentally trigger the neighboring system.
Right. It prevents heat spillover from a fire activating one system from unintentionally triggering a detector located just across the boundary in the adjacent system detection zone. Ensures proper system isolation and activation based on the fire's actual location.
Makes sense for targeted system operation. Specific rules for water cooling towers are also referenced.
Yes, pilot line detection in water cooling towers follows specific requirements detailed in Section 27.26, which addresses that particular hazard.
And finally, how is the piping for the pilot line detectors supported? Does it need the same robust support as the main sprinkler pipes?
This standard provides a practical allowance here. The piping supplying pilot line detectors is permitted to be supported from the same hangers that are used for supporting the main sprinkler or water spray piping system nearby. The standard specifically notes that this typically smaller pilot line piping is not required to meet all the potentially stricter support requirements, referenced as Section 18.5, that apply to the larger main system piping carrying the water flow.
A practical allowance that likely simplifies installation significantly.
Yes, makes it easier to run the pilot lines alongside the main pipes they are controlling.
Wow. We have certainly journeyed through a surprising and incredibly detailed number of specialized fire protection systems today, all guided by the requirements within NFPA 13.
We really have. We started with the familiar wet pipe system, but even there we found fundamental requirements for gauges, relief valves, and clever details like that necessary air vent in metallic systems. Then we spent significant time navigating the world of dry pipe systems, designed for cold environments, exploring the complexities of sizing based on volume or delivery time, the role of quick-opening devices, the critical management of dry air or nitrogen supply, and the vital engineering principles focused on preventing ice plugs, including those recurring tiny purposeful holes in check valves.
Yeah, those holes. Then we covered pre-action and deluge systems, really focusing on the crucial role of the detection system activating first, the different interlock types, single, non-double, dictating when water enters the pipes, and the specific sizing and supervision requirements, particularly noting how double interlock systems provide extra protection against accidental discharge in sensitive areas, and how these systems are adapted for challenging cold environments like freezers.
We also looked at that highly specialized combined dry pipe and pre-action system, typically found in demanding locations like piers and wharves, noting its layered redundancy, fail-safe detection and sprinkler operation, and the intricate parallel valve arrangements featuring those quarter-inch bypasses designed specifically to prevent nuisance trips while ensuring simultaneous operation when needed.
We briefly touched on multi-cycle systems as listed entities and then dove deep into antifreeze systems for localized freeze protection. We understood the critical importance of using listed solutions, the concerns around ESFR compatibility, the necessity of complete draining after water testing, especially with pendants, the requirements for backflow prevention to protect potable water, and the methods for handling thermal expansion using appropriately sized expansion chambers or relief valves for smaller volumes. And yes, we saw that tiny check valve hole appear yet again, this time with a specific note about allowing thermal expansion bleed off.
And then we examined systems tailored for very specific high-consequence hazards. We went through the detailed requirement for protecting commercial cooking equipment and ventilation systems, highlighting the need for targeted nozzle placement in hoods, collars, and ducts, the necessity of using extra high temperature-rated sprinklers, and the absolutely critical function of the automatic fuel and heat shutoff that must activate upon system operation and require manual reset.
And digging into the details relevant to challenging environments, we spent considerable time on the unique difficulties of refrigerated spaces. We learned about the requirements for those removable pipe sections at freezer entries to check for ice plugs, the need for very dry air or nitrogen supplies, specific piping pitch for drainage, the specialized check valve considerations, and the complex environment-specific rules for fire detection within those freezing areas, including detector types, placement within racks, and the specific conditions under which ceiling-only detection might be permitted.
Finally, we explored the application of outside sprinklers used for protecting buildings against external exposure fires, understanding how water needs to be applied effectively to exterior surfaces, the different calculation methods based on achieving a minimum application rate tied to exposure severity, and the specific requirements like corrosion resistance for components and the need for an extended water supply duration, often 60 minutes. And we wrapped up by looking at pilot line detectors, understanding how standard sprinklers can serve as triggers, the different spacing rules required for indoor versus outdoor or open grading locations, and how their support can often be integrated with the main system piping.
It's truly incredible, the level of detail, how deeply the standard goes into addressing every potential challenge, every specific environment. From preventing a minuscule ice plug in a freezer pipe with a cleverly designed removable section in dry air, to specifying the exact temperature rating of a sprinkler head positioned just inches above a blazing hot commercial fryer, to ensuring fire won't easily wrap around the corner of an exposed building by requiring extra heads or linked check valves. Every single detail, down to the precise diameter of a hole you can barely see in a valve clapper, clearly has a critical engineering purpose behind it, all aimed at ensuring the system functions reliably and effectively when it's needed most.
Absolutely. It drives home the point powerfully that effective fire protection is not a simple commodity or a one-size-fits-all solution. It's a highly specialized field of engineering, grounded in science, testing, and decades of experience dealing with real-world fire scenarios in incredibly diverse settings.
Understanding these distinctions, these specialized systems and their nuances, isn't just dry technical knowledge. It really fosters an appreciation for the ingenuity, the rigorous analysis, and the sheer depth of thought that goes into designing systems to protect lives and property from fire in the complex and varied structures we build and occupy.
Well said. It's about understanding the why behind the rules.
So let's leave our listeners with this. What does this all mean for you? Think about a building, well, maybe you have a friend who works in a massive cold storage facility, or perhaps you frequent a restaurant with a very busy kitchen. Or maybe you live in an area where wildfires are a seasonal concern and buildings need robust protection from adjacent exposures. Based on our deep dive today into the specifics of NFPA 13, what kind of fire protection system, or maybe combination of systems, do you think might be needed in that specific location you're picturing?
Yeah. Apply the knowledge.
And considering the incredibly detailed requirements we discussed, maybe for systems operating in constantly refrigerated spaces, or for those protecting high heat cooking equipment, or for systems designed purely for outside exposure protection, why would those specific, often very prescriptive engineering choices we talked about, things like needing specific piping materials or redundant air lines in a freezer, or mandating an automatic fuel shutoff interlock in a kitchen, or requiring a full 60-minute water supply duration for outside sprinklers, why would those precise details be absolutely critical to the overall fire safety strategy and the survival of that particular building you have in mind? Something to think about.